When we have a system of linear equations in three variables that has exactly one solution, it means we have three planes that intersect in exactly one point. In our last example, we saw a system with no solutions. In this example, we're going to see a system that has infinitely many solutions because planes in space can intersect just like these note cards along a common line of intersections. And so the equations that these three planes would represent would have a solution everywhere on that line of intersection. And so I want to show you what that looks like. So again, a spoiler, this system of linear equations doesn't have one solution, it doesn't have no solutions, it has infinitely many solutions. So I thought we'd take a look and see what that looks like. So let's solve this system. I'm going to proceed by elimination. Let's multiply this bottom equation by -1 and add it to the equation that's right there. And so that equation I'll just rewrite with no changes. This equation, I'm going to multiply by -1. Let's add those together, and I would get 2x plus 2y. The z's cancel, equals 5. So now I have an equation here just in x and y. So now let's take this bottom equation, multiply it by -3, and add it to the top equation. And that way I can have another equation that just has x's and y. So I'm going to leave that top equation alone. And this bottom equation, I'm going to multiply by -3. All right, let's add those together. I'm going to get 2y. Skip the x's, don't know why, plus 2, so that'll give me 2x, equals 5. And well, that's the equation I already had, right? And so I could try to eliminate a variable by making any of these a negative that I wanted to, add those together, I get 0 equals 0. Well, that's called a true statement. If I get a false statement, there's no solutions. When I get this true statement, it means there were infinitely many solutions. And what I can do now is describe them. Because what I know for sure now is that 2x plus 2y is equal to 5 for all of the points on this common line of intersection. So I want to give you a recipe that you can follow to find all of those points that live on that line. So let's just let x equal something. Let x equal t, pretending that t is just some number. Well, if I was to plug that in, I would get 2t plus 2y is equal to 5, and I could solve for y. 2y equals 5 minus 2t. Let's divide everything by 2. And y is equal to 5/2 minus t. All right, well, that's a nice start. That tells me that if x was equal to t, you pick a number, x is equal to that number, then y is equal to 5/2 minus that number. And all my recipe is missing now is an answer for z. So I take these two values and I plug them into any of the original equations I want and solve for z. So I'm going to choose that bottom equation. We'll rewrite it here because it's off screen now, but x plus 2y minus 2z equals 3. Well, x is equal to t plus 2 times 5/2 minus t, plugging in for y, minus 2z is equal to 3. All right, t, distribute this 2 plus 5 minus 2t minus 2z is equal to 3. Let's combine our like terms. T minus 2t is a minus t. Let's take 5 away from both sides. So I have minus t minus 2z is equal to minus 2. Add t to both sides. And finally divide by that minus 2. So z is equal to minus 1/2 t plus 1. Every time you choose a value of t, you get a point on that line of intersection. Another way to say that is every time you choose a different value of t, you've solved this system of equations. So this describes those infinitely many solutions.